Okay. More trig substitution. Not to be confused with U substitutions where you're using trig functions. Substitution. So here's what I would say in the hierarchy of what to do, or the flow chart of what to do, if you're looking at an integral, the first thing you should always think of is, can I simplify it? Then if I can't simplify it where I can just integrate it, can I do a nice U sub? And if I can't do that and it's a mixture of things, can I try integration by parts? But if it's not a mixture and you've got something like a square root of 1 minus x squared, or a square root of x squared minus 1, or a square root of x squared plus 1, or 1 plus x squared, these are the kinds of things that think, okay, if we see this, trig sub is usually where it's at if you have eliminated the other possibilities first. Okay, so let's look at some examples. Let's say we have the integral of, sure, how about 1 over x times the square root of 9 minus x squared. So first of all, the 1 was kind of a red herring. It doesn't have to be a 1 minus x squared or x squared minus 1 or 1 plus x squared. It can actually be any constant minus x squared or plus x squared or that x squared minus it. So in this case, in every case with the trig sub, I'm trying to make a trig identity happen. I'm trying to either get 1 minus sine squared equals cosine squared, or 1 plus tangent squared equals secant squared, or secant squared minus 1 equals tangent squared. That is always what I'm trying to make happen. So what I want here is I really want 9 minus x squared. I want that to equal, I want it to equal 9 times 1 minus sine squared. That's what I really want. So the intermediate step is then to say that I really want 9 minus 9 times sine squared. So that my trig substitution is actually going to be x equal to 3 times sine of theta. Because then if we plug that in, our 9 minus 9 sine squared is going to be 9 times 1 minus sine squared, and that's going to equal 9 times cosine squared theta. So that the thing that's inside the square root, instead of being something minus something else or something plus something else, it's just one term that is easily square rootable. So that's not a real word, but we go. Okay. So we're going to make this choice. And then we are for sure going to make sure that we write down dx equal to 3 times cosine theta times d theta. And then we're going to proceed with our change of variables. Every x, especially the dx, has to turn into a theta. So our integral now gets to become, so dx is 3 cosine theta d theta. 1 over x is going to be 3 sine theta. And the square root of 9 minus x squared is going to be the square root of 9 cosine squared. That square does not look great. Sorry about that. Simplifying, we get, well, I can cancel a 3. I get cosine theta divided by sine theta times 3 cosine theta d theta. Canceling a cosine theta, I get 1/3 the integral of, instead of writing 1 over sine, I'm going to write cosecant. And then we have to remember we learned cosecant last time. I should say we learned the integral of cosecant last time. That's going to equal 1/3 times the natural log of the absolute value of cosecant theta plus cotangent theta. Minus, yeah, it's a minus. Sorry about that. Plus negative cotangent theta. Sorry about that. That's terrible. I'll see. We're not done. With any indefinite integral, we better end with the same variable we started with. We started with x's, we better end with x's. This is where we're going to use the triangle. So we're going to use the fact that x equals 3 sine theta, or as I would maybe prefer to write, sine theta is equal to x divided by 3. So if I draw a little right triangle here, where my angle is theta, and sine of theta is the opposite divided by the hypotenuse, then I can find the missing side, bless you, which is going to be the square root of 9 minus x squared. Or you can actually do the work and be like, call it a or something, and a squared plus x squared equals 3 squared, and then solve for a, and you get a squared equal to 3 squared minus x squared, or a is equal to the square root of 9 minus x squared. But it should always, always, always be the square root that made you start this whole process in the first place. That missing side there is always going to be the radical that, oh yeah, that's why we did this in the first place, so that's going to show up, always. And then, to finish the problem, we're going to look at our triangle and say to ourselves, all right, well, cosecant of theta is the reciprocal of sine, so it should be 3 over x minus cotangent of theta. Well, tangent is opposite over adjacent, so cotangent is adjacent over opposite. So it's the square root of 9 minus x squared over x. Let's see. And I guess you could write that as one fraction in your absolute value if you wanted to, but it's not super necessary. Questions or comments before we do some more? So a couple things. I know that when my square root has a something minus x squared or x squared minus something, the subtraction symbol is always going to go with either sine or secant. I have to figure out which one's the right one. Whereas if it's a plus, like x squared plus 9, I know it's going to be tangent because the plus looks like a t and tangent starts with t. Totally works. So let's look at another example. Or my other example, sure. Let's say we want to find the integral of dx divided by x squared times the square root of x squared plus 25. All right. Oh, I don't need another dx there. That's silly. So I want everyone to write down what they think x is supposed to equal. I'll give you a hint. It's 5 times something. We want our choice for x to make it so that whatever we choose for x, x squared plus 25 ends up being a trig identity. The 25 has to factor out. So we need x to be 5 times some trig function. And we know that since there's a plus, it's got to be tangent. So we're going to say that x is equal to 5 tangent theta. And again, the reason for this is that when you plug in x for this x in the square root there, bless you, you're going to get 5 tangent theta squared plus 25, which becomes 25 tangent squared theta plus 25. We factor out the 25, we get tangent squared theta plus 1. And then 1 plus tangent squared is secant squared. So again, the impetus for doing any of this is that we want the thing in the square root to be some trig identity that becomes simpler. So then if we start rewriting this, well, I better first say that dx is equal to 5 times secant squared theta d theta. So now if we start rewriting this, our dx is 5 secant squared theta d theta. Our x squared is going to be 5 tangent quantity squared. And depending on how you like to do this, I kind of like to do all this work over here, but if you really wanted to, you could start off by just writing, okay, yeah, my square root is the square root of 5 tangent theta squared plus 25. And then we simplify. So let's see, I've got 5 secant squared on top. I've got 25 tangent squared right there. And then the square root of this is going to be the square root of 25 secant squared theta. theta. Simplifying further, cancel a 5 here and a 5 here. So I've got, I suppose I'm probably writing more steps than I really need to. Oh, well, secant squared theta over tangent squared theta. And then this, 5 tangent squared theta. I'll put the 5 here. Times the square root of 25 secant squared is 5 secant theta. Simplifying a bit more, I'm going to put the 1 over 25 out in front. My integrand will simplify to secant squared over secant is just secant theta over tangent theta. Theta. Now what? I don't really see a U sub to do. So when I get to this point, you can go a few different directions. I almost always go in the direction of it doesn't seem like it's something I know how to integrate right away. Right? It's not secant times tangent. That'd be great. I'd be thrilled if it was secant times tangent. I usually start rewriting things in terms of sines and cosines. So I'm going to rewrite this as 1 over 25 times the integral of 1 over cosine theta over sine theta over cosine theta. And look, we're going to get the same thing we got last time. We're going to get 1 over 25. Well, I mean, the same trig function. 1 over cosine divided by sine over cosine is the cosines cancel and you get 1 over sine, which is cosecant of theta again. So then we're going to get 1/125th natural log of the absolute value of cosecant of theta minus cotangent of theta. Let's see. And you might say, like, this seems weird, James. Why would this integral and the previous integral essentially have the same answer? Well, they don't. They have the same trig function as their answer, but then when we go back to being in terms of x, the actual argument inside the logarithm is going to be a bit different, right? In the previous one, inside the logarithm, we had 3 over x and square root of 9 minus x squared over x. Here, we're going to have totally different expressions with x in it. So again, doing the funky triangle thing, we're going to say that this is going to give us tangent of theta equal to x over 5. Draw my triangle. Tangent is the opposite over the hypotenuse, opposite over the adjacent. And then the hypotenuse side is going to be the square root of x squared plus 25. So then my final answer here is going to be 1 over 25 times the natural log of the opposite value of cosecant. I never remember. I know sine is opposite of hypotenuse, so cosecant is the reciprocal hypotenuse over the opposite. So it's going to be the square root of x squared plus 25 over x minus, we know that cotangent is going to be not x over 5, but 5 over x. So a little bit different. Kind of weird though. Yeah. Sure. So there's actually a couple things I'm doing that I haven't been saying. So let's back it up for a second. Let me remind you of something that you might have forgotten about from 21A. Sorry. So there's 2 ways I'm doing this, which are kind of related. Who remembers the derivatives of the inverse trig functions? Well, here they are. The derivative, specifically inverse sine, inverse tangent, inverse secant, because the other 3 are really just the same, but negative. So I'll remind you all, the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. The derivative of inverse tangent of x is 1 over 1 plus x squared, or x squared plus 1, either way you like to write it. And the derivative of inverse secant of x is 1 over the absolute value of x times the square root of x squared minus 1. So one way I'm actually making this connection is by saying, oh, if I see a 1 minus x squared, I know it's sine. If I see 1 plus x squared, I know it's tangent. And if I see an x squared minus 1, I know it's secant. And if it's not 1, right, like if it's a 9 minus x squared, x is going to be 3 times sine. And if it's a 9 plus x squared, x is going to be 3 times tangent. And if it's a 16 x squared minus 16, it's going to be x equal to 4 times secant. Also, this is coming from the fact that 1 minus sine squared theta is equal to cosine squared theta. 1 plus tangent squared theta is equal to my secant squared theta. Secant squared theta minus 1 is equal to tangent squared theta. So there is a nice connection between the derivatives of the inverse trig functions and what you're choosing for your trig substitution. Not coincidentally, right? This is very much because of the way things are defined. But it makes it kind of easier to be like, okay, if I know these, I know what to guess. But really, we're just trying to make the trig identity happen. So, yeah. For example, let's say that probably not a whole other piece of paper. Yeah. So let's say we were faced with this next problem. The integral of dx over, sure, that looks gnarly, x to the fourth times the square root of x squared minus 9. And let's say for just a second we chose wrong. So I know it's not tangent because I know tangent goes to the plus sign. But let's pretend like I made the wrong choice. And I said, I'm going to let x equal 3 sine theta. Let's see what happens if we go the wrong way, where we end up. Well, specifically for the square root here, x squared minus 9 is going to be 3 sine theta squared minus 9, which is 9 times sine squared theta minus 1. What's sine squared theta minus 1 equal to? It's not quite cosine squared. It's actually the negative of cosine squared. And that becomes problematic because if you have 9 times negative cosine squared, and then you're trying to take the square root of that, it's always negative. The square root of 9 times negative cosine squared is imaginary. Does not work. So if you make the wrong choice, eventually you get to a place where you either don't have a trig identity. Like if we'd chosen x equal to tangent, we would have encountered similar problems. We'd have had tangent squared minus 1, which isn't a trig identity. So if you make the incorrect choice, you'll get to a place where you don't have a nice trig identity. But again, I'm thinking, oh yeah, I know that when it's x squared minus 1 or x squared minus 9, that derivative went with inverse secant, so my choice should be secant. So we're going to pick x equal to 3 times secant of theta. Which means our dx is going to be 3 secant theta tangent theta d theta. When we start plugging things in, we've got a lot to do here. So our integral is going to become 3 secant theta tangent theta d theta over x to the fourth, which is 3 secant theta to the fourth power times the square root of, instead of writing 3 secant theta quantity squared, I'm going to write 9 secant squared theta minus 9. We start simplifying. You can cancel one of the secants already. So I have the integral of, sure, 3 times, I suppose I could have canceled the 3 as well. Oh well. 3 tangent theta over 3 to the fourth times secant cubed because I canceled one of the secants. And then the square root of 9 is 3. The square root of secant squared minus 1 is tangent theta. That's what's going on there. D theta. Cancel another 3. Cancel a tangent. So now I've got the integral of 1 over 3 to the fourth, which is 1 over 81, times 1 over secant cubed. Which I should probably rewrite as the integral of cosine cubed. And now we have to do a u substitution. And u is going to be equal to sine of theta. We did this one last time, or we did one similar to it last time, where when you have an odd power of cosine and an even power of sine, you pick u to be the one that's to the even power. and we have sine to an even power, we have sine to the 0th power. But the more natural way of doing this is to rewrite it as cosine squared theta times cosine theta d theta, and then rewrite that as 1 minus sine squared theta times cosine theta d theta. I guess I could use that room there. Oh well. And then we're going to let u equal sine, and our du is going to be cosine. So u equals sine theta, du is equal to cosine theta, d theta. So we end up getting, sorry, all over the place here, apologies. So our integral becomes 1 over 81. Integral of our cosine theta d theta is our du. Our 1 minus sine squared is 1 minus u squared. We integrate. We get u minus u cubed over 3, which then becomes sine of theta minus sine cubed theta over 3. Let's see, and then we plug that, well, then we have to do the triangle thing. So we had x equal to 3 secant of theta. So secant of theta equals x over 3. Secant is the reciprocal of cosine, which is adjacent over hypotenuse. So it's hypotenuse over adjacent. So here's my funky triangle. And the hypotenuse is x. The adjacent is 3. The missing side is, I don't know, 3 squared plus question mark squared equals x squared. So question mark squared equals x squared minus 9. So my question mark is the square root of x squared minus 9. Oh, wait, it's just the thing that's already in the integral, right? There it is. That should have told me that that's going to be my missing side. It always works, right? If you're doing a trig sub, with one exception, there'll be a radical. And the radical will tell you what's the missing side of your triangle. There is one exception, which we will eventually get to, which is terrible, but we'll talk about it. So this ends up equaling 1 over 81 times sine of theta, which is the opposite of the hypotenuse. So that's going to be the square root of x squared minus 9 over x minus 1/3 times sine cubed, which is going to be this quantity cubed. So x squared minus 9 to the 3/2 power divided by x cubed. It's kind of bizarre. These trig substitutions always feel kind of bizarre. They do get weirder. Let me show you another one. Let's try this one. The integral of x over the square root of x squared plus 16. So what's my trig sub? Tangent. Except it's a trap. So I know we've been trig sub the whole way here, but I'll remind you before. So I refer to trig substitution as kind of a method of, not a method of last resort, a method of later resort. You should definitely be looking for other things first. And in this example, we could for sure do an easy u sub because the top is essentially the derivative of the inside of the square root. So you should always rule out a u sub before you start trying trig sub. So here we'd let u equal x squared plus 16. Your du would be 2x dx. 1/2 du is equal to x dx. So this integral becomes the integral of 1/2 du divided by the square root of u, which is 1/2 the integral of u to the negative 1/2, which becomes 1/2 times u to the 1/2 divided by 1/2 plus c, which is just the square root of u, which is the square root of x squared plus 16. Get this pen's out of ink. You could have done this one with the trig sub. It would have been a lot more work. But if you have the time and the wherewithal, I encourage you to try it out. It is kind of interesting to look the other way, but it does end up being a lot more work. Let's see. There's one I wanted to make sure I did. I think it was that first one we did. Let's go back here for a second. And something I want to make sure you all see because it can be kind of a pain in the butt. Go. Oh yeah, that one. Sure, yeah, you're fine. Okay, we can do that one, I guess. Yeah, all right. Yeah, okay. So let's look at another example, one that actually is a trig substitution and not just a trick. So let's say we have the integral of square root of 36 minus x squared. All right, I want you all to write down the trig substitution. And I should actually, I'll point out that the more general kind of guidelines here are if you see a squared minus x squared, you're going to write or make the trig substitution x equal to a times sine theta. If you see a squared plus x squared, you're going to let x equal a times tangent theta. And if you see x squared minus a squared, you're going to let x equal a times secant theta. So in this case, you all should be able to see that you're going to let x equal some multiple of some trig function. So find your x, find your dx, rewrite your integral in terms of theta. So if we make these choices where x is 6 times sine theta and dx is 6 times cosine theta, we get the integral of the square root of 36 minus 36 sine squared theta times 6 cosine theta d theta. 36 comes out, the square root of 36 is 6. Square root of 1 minus sine squared should end up becoming cosine. And then we have another 6 times cosine. So we end up getting the 36 times the integral of cosine squared theta. Cosine to an even power. Gotta use that trig identity where it's 1 plus cosine of 2 theta divided by 2 theta. Bring out the 1/2, you get 18. Integrate 1, you get theta. Integrate cosine 2 theta, you get sine 2 theta divided by 2. So again, using our funky triangle, we have that sine of theta is equal to x divided by 6. By the way, if you don't have a thing like if sine of theta is just equal to x, we're going to write sine of theta equals x divided by 1 so that the opposite is x and the hypotenuse is 1. Here the opposite is x and the hypotenuse is 6. And the missing side is going to be, of course, the square root of 36 minus x squared. But I have a problem. I have sine of 2 theta, not sine of theta. To get around this problem, we have to use the double angle identity for sine. So this ends up being 18 times theta plus 2 sine theta cosine theta. That's the double angle identity for sine, and then still divided by 2. So I end up getting, and I should have a plus C, terrible. I end up getting 18 times, what's theta? Well, if sine of theta is equal to x over 6, theta is equal to the arc sine or the inverse sine of x over 6. There's nothing else to do except write that. And we have 18 times sine of theta, which is x divided by 6, times cosine of theta, which is root 36 minus x squared divided by 6. Plus c. I won't lie. I think this is fun. I really like. I'm like, these are so like. It's just neat to do this. Like, oh yeah, all the trig identities come out, and you get some cool stuff happening. It's kind of neat. There's two more trig substitution problems I want to throw at you, and then we'll talk about partial fractions. Two more, yeah, just two more. So, yeah, let's look at this next one, which is, well, we'll talk about it. So let's say we had the integral of, where'd you go? Sure. The integral of x cubed over the square root of, we can go either way here, really. Sure, let's go x squared minus 1. Could I do a trig sub here? For sure. I could let x equal secant of theta. But I could also do a u sub with a back sub. And it's kind of a matter of opinion which way is the easier way to go. I would probably choose u sub with a back sub, although it might be harder to see that at first. So if you see a potential choice for u and you see that power of x doubled minus 1, so I see x squared and I see x to the 2 times 2 minus 1, which is 3, that usually means you can do a back sub relatively easily. In a similar way, if you had something like the integral of x to the 5th times the square root of x cubed plus 1, this for sure would be a u sub with a back sub. And you couldn't do a trig sub here because you don't have x squared, you have x cubed. I mean, you could probably make a trig sub happen if you really worked at it, but it would be sucky. So I would rather do a u sub with a back sub. We're going to let u equal x squared minus 1. Our du is 2x dx. 1/2 du is x dx. And I can rewrite my integral as x squared over the square root of x squared minus 1 times the other x times dx. My x dx is my 1/2 times du. My x squared minus 1 is my u. And my x squared, well, if u equals x squared minus 1, u plus 1 equals x squared. So that's going to equal u plus 1. So my new integral is u plus 1 divided by the square root of u times 1/2 du. Pull the 1/2 out in front. U divided by root u is root u, or u to the 1/2. 1 divided by root u is u to the negative 1/2. Anti-differentiate, you get 1/2 u to the 3/2 times 2/3 plus 1/2 u to the 1/2 divided by 1/2 or times 2 plus c. Simplify and plug back in. You're going to get 1/3 times x squared minus 1 to the 3/2 plus 1 times the square root of x squared minus 1 plus c. It's probably better than doing a trig sub, but I don't know. It might not have been. It's hard. It's really hard to say without doing it the other way, but why would we do it again? Because it's fun. No, I'm not going to do it again. I don't think any of your instructors are crazy like this, but sometimes is either professor doing web work? No. What? Parlac is? Okay. All right. So, and I know you guys are totally not on this stuff yet, but you're going to be eventually. So definitely this is going to come up eventually. And for those of you in Parlac, after this week, we're going to swing back around and start talking about areas, volumes, and the other physical things. So sometimes, and I have to think about this for a second here, people do crazy things like the following. The integral of, let's not make it too crazy. Sure. Let's say, yeah, I'll make it real, not crazy. 1 over the square root of, I forgot to think about what it was going to be. Give me 1 second here. Sure. Cool. So something like this. Negative x squared plus 2x plus 3. You see something like that, you're like, what are you doing? So when you see a quadratic in a root, and it's not like x squared plus 1 or x squared plus 9, or it's not like a difference or a sum of seemingly looking squares, usually what that means is you have to complete the square. Usually. So here's what we're going to do. We're going to write this as 1 over the square root of, I'm going to pull out the negative and write it as negative parentheses x squared minus 2x. I'm going to leave myself a little bit room. And then the plus 3 is still just plus 3 hanging out here. So for x squared minus 2x, what do I need to add on to complete the square? I know it's been a minute. You take your negative 2, you divide it by 2, and you square it, which is going to be positive 1. But I can't just add 1. I also have to subtract 1. So I'm going to add 1 and subtract 1. And the reason I wrote that inside the parentheses is to make sure that the 1 we're subtracting, which is going to come out, is actually a minus 1, which is plus 1. It's extra crappy. So, sorry, I forgot the integral symbol here. So look what we've got now. It's the integral of 1 over the square root of, check this out. I don't really want that minus 1 in there. I just want this part because the x squared minus 2x plus 1, that's the part that's equal to x minus 1 squared. So I'm going to rewrite this as, sorry, negative parentheses x minus 1 squared, and then the minus 1 is plus 1, plus 3 is plus 4. Or written slightly in a different order, the integral of 1 over the square root of 4 minus x minus 1 squared. Which looks a lot like an a squared minus an x squared. So you could do one of two things at this point. You could either first do an easy u sub. You could let u equal x minus 1. And then do the trig sub. Or you could just do the trig sub right away. So one option is u sub first. We would let u equal x minus 1. Our du would equal dx, which I forgot to write up there. And then our integral will become the integral of 1 over the square root of 4 minus u squared du. And then you would do the trig substitution. Actually, you really wouldn't. So here's what I'd say about this particular example. Technically, you kind of know the answer already. We know that the derivative of the arc sine of x is 1 over the square root of 1 minus x squared. So the integral of 1 over the square root of 4 minus x squared should be 1/2 arc sine of x over 2. Sorry, u over 2. Is that something we should memorize? Maybe. I don't know. I'm not the one teaching the class. Or you could have made this other choice and said, well, I'm just going to make my trig sub right away. And my trig sub is going to be, well, I want this stuff, x minus 1, to equal 2 sine theta. It's kind of weird. But then we can solve for x. X equals 2 sine theta plus 1. Our dx is 2 cosine theta d theta. And then our integral becomes the integral of 1 over the square root of 4 minus x minus 1 is going to be 2 sine theta squared times my dx, which is 2 cosine theta. 2 theta. Now here's where something kind of fun happens. We're going to end up getting the integral of 2 cosine theta d theta over the square root of 4 minus 4 sine squared is really 4 times 1 minus sine squared, which is 4 times cosine squared theta. And everything cancels. We get the integral of 1, which is what? Not x, it's got to be the variable you're working with. It's theta plus c. And then since 2 sine theta is equal to x minus 1, we can say that sine of theta is equal to x minus 1 divided by 2, and theta is equal to the arc sine of x minus 1 over 2 plus c. I hope you don't get to see that. But if you do, you know how to approach it. So sometimes people do, especially web work. Web work does some weird, gnarly things with trig substitution, and sometimes gives you funky quadratics where you first have to complete the square and then see the trig sub. If you see that, come see me. I'm happy to help, as you can tell. I really enjoy this stuff. So that's pretty much all there is to say about trig substitution. Again, it's a method of later resort. You should first look for a u sub and or a u sub with a back sub before you start going down this path. And the indicators for a trig sub are, with one exception, which I promise you I will eventually show you, should be a radical with a something squared minus x squared, or an x squared minus something squared, or something squared plus x squared. And a radical could mean a square root. It could mean something to a 3/2 power. It could be something to a 5/2 power. Your power could be anything where it's a radical with a 2 as the denominator. And I saw a hand back there. No. Oh, I have not. Thank you so much. It's just sitting right in front of me. I'm like, you should pen anything out. I keep forgetting because I'm so excited about the trig substitution. Okay. So that's most of what there is to say about trig substitution. I mean, I could go on, but I shouldn't because we've got this whole other thing to talk about, partial fractions. Partial fractions. There you go. Cool. So, whereas trig substitution is kind of like a u sub thing, I would liken partial fractions more to integration by parts, which is too bad because they both have the word parts in them, and it's easy to say the wrong thing, in that you're taking an integral and trying to make it easier to write. Except you're not going to write it with a new integral. You're going to simplify the integrand in kind of a special way. So let's look at some examples of partial fractions. So partial fractions really is an exercise in algebraic manipulation, not so much integration. So partial fractions. We're going to do all the things. What time is it? Okay, yeah, we got time. So let's say we have this 2x plus 5 divided by x squared plus 4x plus 3. So before I get going here, I should make sure a u sub isn't easy to do, because like in trig substitution, partial fractions is also a method of later resort. U sub should always be your go-to. Like, can I do a u sub? No, try something else. But you should always be thinking in the back of your head, u sub, u sub, u sub. Can I do a u sub? Okay, I couldn't. Move on. And I couldn't here, because if I let u equal the bottom, my derivative would be 2x plus 4, and 2x plus 5 is not an easy multiple of that. So we're going to try partial fractions, meaning we're going to do a partial fraction decomposition of the thing inside our integrand. Now, to do this, 3 things have to be true. The integrand has to be a rational function. So 1 must be a rational function, meaning a polynomial divided by another polynomial. 2, the degree on top must be strictly less than the degree on the bottom. And 3, the denominator must factor. And in this case, all 3 things are true. It's certainly a rational function. The degree on top is 1, the degree on the bottom is 2, and the denominator does factor as x plus 3 times x plus 1. So then, to do the partial fraction decomposition, here's what we do. We're going to break up the fraction into simpler fractions. So we're going to say that our original rational function, which I'm thinking of as a fraction, 2x plus 5 over x plus 3 times x plus 1, can be written as the sum of fractions that will end up having the same common denominator. So I'm going to say, cool, this is going to be some number divided by x plus 3 plus some number divided by x plus 1. Because if I add those two fractions together, I have to multiply a by x plus 1 over x plus 1, a over x plus 3 by x plus 1 over x plus 1, and b over x plus 1 by x plus 3 over x plus 3, so that I can add those fractions and have the common denominator, which is x plus 3 times x plus 1. So basically, you look at all the factors in your denominator, and then you write your decomposition as kind of all those factors showing up. There's a little more to say about that in a minute, but for now, this is what it is. So the way we always go about solving this, in my opinion, is we then multiply both sides of this equation by the common denominator. So then I'm left with the equation, whatever the numerator was on the left, in this case 2x plus 5, equal to, when you multiply x plus 3 times x plus 1 by the first fraction, the x plus 3's cancel, and you get a times x plus 1. Similarly, when you multiply by this second part, you get b times x plus 3. Some people like to make this more complicated than it needs to be. I do not. This equation is supposed to be true regardless of the value of x. Meaning, you can pick any value of x and then plug that in for x and solve for what's left. Specifically, I could pick x equal to negative 1. And if I pick x equal to negative 1, on the left-hand side, I have negative 2 plus 5 equal to, on the right-hand side, a times 0 plus b times negative 1 plus 3. That was convenient. The a went away. And I have 3 equal to 2 times b, or b is equal to 3 divided by 2. Similarly, I can make a really easy choice or convenient choice of x to solve for a. If I chose x equal to negative 3, I'm going to get 2 times negative 3 plus 5 equal to a times negative 3 plus 1 plus b times 0. So then negative 6 plus 5 is negative 1 equals a times negative 2. So a is equal to positive 1/2. Alternatively, some people might not show you this. I don't know why they wouldn't. And they might say, we can do this thing where we equate coefficients. If you multiply out the right-hand side here, you can say that, Charles Rounds would be thicker here. You have on the left 2x plus 5. On the right, you have ax plus a plus bx plus 3b. And then 2x plus 5 equals a plus b times x plus a plus 3b. And then you can set up a system of equations where a plus b has to equal 2. And a plus 3b has to equal 5. And then you can solve that system by, I don't know, like solving for a here and plugging it in there. Like a equals 2 minus b, plug that in over there. You get 2 minus b plus 3b is equal to 5. So 2 times b equals 5 minus 2. So b equals 3/2. And then plug that back in over here. And 2 minus 3/2 equals a, which equals 1/2. The same things we got right there. Here's the point. This is not bad. This is great when we need it. Because sometimes we're going to do this and we're going to run out of convenient values to pick that make one thing 0 and everything else not, or vice versa. Everything else 0 and one thing not. But I would say when you're trying to solve partial fraction decompositions, you should start with picking the convenient values of x that make things 0 and go away. And then if you run out of those things, then start thinking about equating the coefficients of x or x squared or x cubed or whatever powers of x are showing up. We will see this more in a minute. For this problem, our integral of 2x plus 5 over x plus 3 times x plus 1 is now going to become the much, much easier integral of a over x plus 3 plus b over x plus 1, which is going to be 1/2 times the natural log of the opposite value of x plus 3 plus 3/2 times the natural log of the opposite value of x plus 1. Let's see. So the whole idea is that once you've rewritten it as the decomposed partial fraction decomposition, the integral is much simpler to find. On the other hand, if I had asked you, and I'm asked this question in the jerkiest way possible, if I had asked you to find the integral of 5x plus 10 over x plus 3 times x plus 1 dx, I've written this in a way that is really trying to induce you to use partial fractions because I factored the bottom already. That's often a clue that you should actually use partial fractions. Here it is not. Here it is me trying to be cruel and make you do the wrong thing. Because really, if we multiply out the bottom, we have x squared plus 4x plus 3. And here, if we do a u substitution, if u is x squared plus 4x plus 3, my du is 2x plus 4 times dx. And if I factor out a 2 there, du is 2 times x plus 2 dx. And in my integral, I can factor out a 5. My integral is equal to 5 times the integral of x plus 2 times dx over x squared plus 4x plus 3. So really, I should write this as 5 times the integral of, let's see, du divided by 2 is my x plus 2 dx. And my bottom is just u. The moral of the story being, look for the u substitution. Unless it's really, really obvious, you can't do one. So here we're just going to get 5/2 natural log of the opposite value of u, which is 5/2 natural log of the opposite value of x squared plus 4x plus 3 plus c. So be on the, you should, when you're integrating, you should be like on the lookout. Be alert for a u substitution. It might be hiding somewhere. Look for it. But then sometimes there is. So let's look at some other stuff. So we're not going to do this next integral, but I'm going to point out the more general idea. So if I was trying to integrate something like 2x plus 1 over, this is going to be really awful, x minus 1 cubed times x squared plus 9 times x plus 5. I just want to show you what the partial fraction decomposition would be so that you know what you're supposed to do for all the things. So any linear factor just gets to be by itself. So x plus 5 is a linear factor. It's going to have an a over x plus 5 or whatever letter we get to. So when we write the decomposition here, I will point out this denominator is fully factored. It cannot be factored any further. X squared plus 9 does not factor over the reals. If you wanted to factor it, it'd be x plus 3 times I times x minus 3 times I. But we are not dealing with the imaginary numbers in this class. Yeah, eventually, but not in this class. So we're going to write this as, and it doesn't really matter what letter you pick for which thing. I'm going to pick the easiest part first, the x plus 5. Now, when you have a linear factor that is raised to a power, or what we call a repeated linear factor, you're going to write that highest power and every lesser power. So we're going to say b over x minus 1 cubed plus c over x minus 1 squared plus d over x minus 1 to the first. Again, we're not going to actually do this problem. We're just showing how you would write out the partial fraction decomposition. We're not going to solve it. It's terrible. Finally, this piece here, which is called an irreducible quadratic factor. You should think of it as a parabola that does not cross the x-axis. This parabola has no zeros. You couldn't factor it. It's an irreducible quadratic factor. For the irreducible quadratic factor, you don't just get a constant divided by x squared plus 9. You have a linear function as your constant, meaning you have an e times x plus f. Kind of gross, but it's necessary. Quick question. Is x squared minus 7 an irreducible quadratic factor? Irreducible quadratic factor? Can you factor that? Let me rephrase my question. Can you factor that over the reals? Meaning using any real numbers, not imaginary numbers, does this factor? And the answer is yes. The better way to ask this question though is, does that parabola cross the x-axis? It for sure does. You've taken your regular one and shifted it down 7. What are the x-intercepts? What are they? Tell me. Set that equal to 0. Bring the 7 over. The x-intercepts are the square root of 7 and the negative square root of 7. So this factors. It factors as x minus root 7 times x plus root 7. You usually don't see this, but I wouldn't put it past either of your instructors to give you that as something that factored. So be careful when you use the word factor. What it really means is you can break up your polynomial into linear factors where it's x minus a real number times x minus a real number times x minus a real number, even if the real number is irrational. It's just less nice. Usually you're not going to see that, but again, I've seen people do it, so I just wanted to warn you. Irreducible quadratic factors are ones that do not have any real zeros. They cannot be factored. They usually look like x squared plus 9, but they could also look like, for example, let's make it easy, x squared minus 2x plus 5. It sure is irreducible. Because if you complete the square, it's x squared minus 2x plus 1 minus 1 plus 5, which is x minus 1 squared plus 4. And that parabola has a vertex at 1, 4 and opens upwards. So it never hits the x-axis. Or you can use the quadratic formula and see that there's no real zeros. Okay, back to the actual thing we're doing. Sorry, I got kind of on a tangent there. So let's look at something more reasonable, more rational. Funny, right? Because it's a rational function. Or not. 3x minus 8 over x cubed minus 4x squared. So this rational function, the u sub would not be good here, right? My u would be x cubed minus 4x squared. My du would be 3x squared minus 8x. Technically, you might be thinking, well, James, I kind of have that, but I'd have to multiply by x, and that's not going to work out. So U step is not going to fly here. So it meets all the criteria. My fraction is rational. It's a rational function. My degree on top is less than my degree on the bottom, and the bottom does factor, and fully factored, it's x squared times x minus 4. So for the x squared, now I'll point out x squared is not irreducible. It definitely equals 0 when x equals 0. It is a linear factor, x minus 0 squared. We don't write it as x minus 0. So this x squared, I need an a over the highest power of it, and then I need every lesser power down to 1. And then I'm going to have a c over x minus. And now we're going to multiply both sides by the common denominator. I'll point out, whenever you have a repeated linear factor, like we do here, you're always going to run out of nice values of x to help you solve for a, b, c, and d. So multiply both sides by our least common denominator, x squared times x minus 4. When we do that, we're going to get, we always just get the numerator on the left-hand side. On the right-hand side, we're going to get a times x minus 4 plus b times x minus 4 plus c times x squared. We should still start by picking the nice values of x. My first nice value of x in this case is x equal to 0. So I plug in 0 for x, I get negative 8 on the left. I get a times negative 4 plus 0 plus 0. We shouldn't even write that. Don't write plus 0. So then a is going to be 2. Awesome. And then my next nice value of x is x equal to 4. On the left-hand side, I get 12 minus 8. On the right-hand side, I get 0 plus b times 4 times 0 plus c times 4 squared. So I end up getting 4 equal to 16c. So c is equal to 4 divided by 16, or 1/4. But now I have run out of convenient values of x. Right? There's nothing else I can pick for x that's nice, that's going to make lots of things 0. You do have a choice here, which I don't love. You could pick another value of x and plug in your a and your c value and solve for b, since there's only one thing left to find. If there's only one thing left to find, it's usually pretty safe to just plug in some other value of x. I don't recommend it, though, because sometimes you're still dealing with gross fractions. There's a better way. The better way is to equate coefficients. And the smart way to do this is by starting with the highest power of x on either side. What's the highest power of x on either side? X to the, I think I see an x squared, right? The reason you want to pick the highest power is because there's usually going to be the least number of terms that have that power. So if we look at x squared, okay, this is going to sound kind of like a dumb question, but go with it. On the left-hand side, what's the coefficient of x squared? Is there any x squared? So if there's no x squared, its coefficient is 0. On the left-hand side, we have 0 times x squared. On the right-hand side, I'm not going to actually multiply it out. But if I did, what would be my coefficients of x squared? Well, I don't have an x squared here, so not a. But I do have b times x, which would be a b times x squared. And I do have c times x squared. In other words, since these polynomials have to equal each other for any value of x, all of the powers of x have to have the same coefficients, which means that 0 must equal b plus c. And since we know that c is equal to 1/4, b must equal negative c, which is negative 1/4. That is the slickest way to do it, in my opinion. It's the most efficient way of doing it, is what I should really say. So cool. We have found all of the constants. Now we're going to go back and rewrite our integral as, instead of the integral of 3x minus 8 over x squared times x minus 4, we're going to write it as the integral of a over x squared plus b over x plus c over x minus 4. We have the integral of a, which was 2 over x squared, plus b, which was negative 1/4 over x, plus c, which is 1/4 over x minus 4. For any denominator that's linear, you're just going to do the natural log thing. But for any denominator that's some other power of x, we're just going to use the anti-power rule, right? This is really 2 times x to the negative second, and its antiderivative is 2 times x to the negative first divided by negative 1, minus 1/4 times the natural log of the opposite value of x, plus 1/4 times the natural log of the opposite value of x minus 4, plus c. And yes, I could simplify that as like negative 1 over 2x or negative 2 over x, but I didn't. Okay. Yeah, let's do how much time we got? Okay, we got probably that much. Sure, let's do one of those. Oh yeah, I guess we have 2 more problems. Yeah, cool. So let's try out. It looks so boring. Oh, fine. Let's try out the next one here. The integral of x plus 1 over x cubed plus x. Again, I'm quickly mentally checking for a u sub. Not going to work. If u is x cubed plus x, my du is 3x squared plus 1. I definitely don't have that or a nice integer multiple of it, or I should say constant multiple of it. So that's not the way to go. So partial fraction decomposition, I have x plus 1 divided by the bottom factors as x times x squared plus 1. That's the most factoring I can do. So my partial fraction decomposition is going to look like a over x plus, for this irreducible quadratic factor, bx plus c over x squared plus 1. So now we're going to multiply both sides by the common denominator like we do every time. On the left-hand side, I'm just going to get the numerator, x plus 1. On the right-hand side, I get a times x squared plus 1 plus bx plus c times x. So usually people ask, not usually, sometimes people ask, but I should explain. People are like, why do you need the cx plus the bx plus c there? Why can't it just be c? And the reason is, well, check it out. If this were just c, fine, kind of in the way here. If that were just c, right? If you only had an a times x squared plus 1 plus a c times x, well then c would have to be 1, so that you have a 1x on the left and a 1x and a 1x on the right. And a would have to be both 0 and 1 at the same time, so that you got 0x squared on both sides and 1 on both sides. So the problem is if you don't have that b there, that bx, you have an unsolvable system. You are going to have problems finding the value of a because a has to fill 2 roles. Or if you have that b times x there, then, oh, really, we know that a has to be 1 and a plus b has to be 0. Even though I'm equating coefficients when I do this, right? That's literally the words I'm saying. I'd still probably do it the other way. I'm a big fan of picking the nice values of x. There's only so really, in this one, there's only one nice value of x. Pick x equal to 0. You get 1 on the left. You get a times 1 on the right, plus 0 times that. So a equals 1. This one's probably better if you just multiply it all. Usually I don't do this, but in this case, I'd probably go ahead and write it out as x plus 1 equals ax squared plus a plus bx squared plus cx, and then rewrite it as x squared times a plus b plus c times x plus a. So clearly, a has got to be 1. C has got to be 1. And a plus b has to be 0. So a equals 1. C equals 1. A plus b equals 0. And a equals 1 means that b equals negative 1. So it's really nice. Sometimes you can just do it like that, I guess. You can clearly tell that I prefer to do it the other way. I'm disappointed it works out so nicely to do it the other way here because I think you should do the thing where you plug in the nice values of x first, because usually that's going to be much, much, much quicker. This is an exception. So here's what we're going to integrate. We're going to be integrating a over x plus bx plus c over x squared plus 1. So that's going to be negative x plus 1 over x squared plus 1. Okay, here's what always happens. Whenever you have this, you always have to break this up as the bx thing over the bottom plus the c thing over the bottom. So we always break up a linear factor over an irreducible quadratic as the x part and the constant part as separate fractions. So it's going to be minus x over x squared plus 1 plus 1 over x squared plus 1. This part is always going to be some sort of arctangent. This part is always going to be a u sub. Every time. No exceptions. I think. I'm pretty sure. I know I was very emphatic about it there, but I'm pretty sure. So, and I'm just going to skip the u sub here. The integral of 1 over x is the natural log of the absolute value of x. The integral of this should be something with the natural log of the absolute value of x squared plus 1. If I take the derivative of that, I would get 1 over x squared plus 1 times what? Right, but I only have an x, so I need a 1/2 to make it all work out. We could have done the u sub, right? You could have done u equal to x squared plus 1. du is 2x dx. 1/2 du is equal to x dx. That's where that 1/2 is coming from. And finally over here, the integral of 1 over x squared plus 1 is the arc tangent of x plus c. Okay. Yeah. Up there in always for any of these problems. Sorry. Not always. So to pick x equal to 0 as one of your nice points, it often will be, but only if x or x to a power is a factor. So in this one, we chose x equals 0 because we had x as a factor. And in the previous ones, we've also chosen x equal to 0, right? X was a factor here. X wasn't a factor here, so we wouldn't have chosen x equal to 0 in this terrible one we did. And in the very first one, we didn't choose x equal to 0, right? X equal to 0 was not a choice here. In this very first one, we chose x equal to -1 and x equal to -3. So no, not always. Just a lot of the time, because often it's easy to make up problems where x is a factor. And so the problem we're not going to get to today, but I just want to mention, yeah, sorry. So I'll just tell you. So note the integral of 1 over x squared plus 1 squared is terrible. It is a trig sub problem. This is a trig sub where you let x equal tangent theta. It is really not fun. Or really lots of fun, depending on your perspective. But it's a problem we're going to not do right now because it is terrible. But I do want to show you one more partial fractions problem. The reason I pointed out here is because it kind of looks like you might think about it as a partial fractions problem, but it's not a partial fractions problem. At least not from the get-go. It's a trig sub from the first. I actually, now that I'm looking, I'm like, I don't remember exactly how it goes, but we'll talk about it if you want to next time. We probably won't talk about it at all because it's really heinous. But come to me in office hours, and I'll definitely talk about it. Anyway, the last problem I want to show you is one more thing that happened. So the point there being, though, that if you had something else over x squared plus 1 squared, then you would have you'd break it up as a ax plus b over x squared plus 1 plus a cx plus d over x squared plus 1 squared. But since the top here is just 1, there's no need to do all of that, I think. Now I'm actually, I'm not sure about that. I don't think that's I don't remember. I'm going to work on this on my own. I'll come back to you and let you know about it. Don't worry about this one for now. The one I wanted to show you is not that one. Where'd you go? Not that one. Where'd you go? None of these on here. Sure, that's cool. Is it the last one? Fine, let's make one up. So sometimes you have something like this: the integral of x cubed plus x over x squared minus, sure, that's going to be awful, minus 3x minus 4. Is that bad? No, that's fine. Okay, cool. So, does the bottom factor? Yes. Is it a rational function? Yes. Is the degree on top smaller than the degree on the bottom? Obviously not. So before you can start even thinking about going down the path of partial fractions, we have to do polynomial long division. So we're going to say x cubed plus 0x squared plus x plus 0, I guess, divided by x squared minus 3x minus 4. Let's see, x times x squared is x cubed, so we get x cubed minus 3x squared minus 4x. We subtract 0. 0 minus minus 3 is positive 3x squared. X minus minus 4x is 5x. Bring down the 0, repeat the process. We need a 3 times x squared to give us a 3x squared. A 3 times negative 3x is negative 9x. And a 3 times negative 4 is negative 12. We subtract 0. 5 plus 9 is 14x. 0 plus 12 is plus 12. So then we can rewrite the integral as the integral of the quotient x plus 3 plus the remainder 14x plus 12 divided by the divisor x squared minus 3x minus 4. And then you can break it up as an easy integral of x plus 3 plus the integral of 14x plus 12 over the denominator x minus 4 times x plus 1. And I should check, because sometimes people do this tricky stuff. Sometimes they'll write something terrible like this, and then when you do the division, this part here, it'll end up being like 2x minus 3 over x squared minus 3x minus 4. And then it's just a u sub. So definitely check when you've got this leftover part here that's maybe going to be terrible, make sure it's not an easy u sub. Always be on the lookout for a u sub. But it's not, because if u is the bottom, du is 2x minus 3, and this definitely isn't a multiple of 2x minus 3. So then for this part here, we would do a partial fraction decomposition. I probably don't. Yeah, sure, fine. So we're going to get x squared over 2 plus 3x plus whatever the integral of 14x plus 12 over x minus 4 times x plus 1 is. We would do the usual thing. 14x plus 12 over x minus 4 times x plus 1 is equal to a over x minus 4 plus b over x plus 1. Multiply both sides by the common denominator. You get 14x plus 12 equal to a times x plus 1 plus b times x minus 4. Set x equal to negative 1. You get negative 14 plus 12 equal to a times 0 plus b times negative 5. So you get b equal to 2/5. Set x equal to positive 4, you get 56 plus 12 is 68, equal to a times 5. So a is going to equal 68 over 5. So then our answer is equal to x squared over 2 plus 3x plus the integral of 68/5 over x minus 4 minus 2, plus, that's a plus, not a minus, 2/5 over x plus 1. And then we can easily integrate that. We get x squared over 2 plus 3x plus 68/5 natural log of the absolute value of x minus 4 plus 2/5 natural log of the absolute value of x plus 1 plus c. So if your degree on top is bigger than or equal to your degree on the bottom, division first. So just as a quick extra comment here, this integral, x squared over x squared plus 1, is really easy if you do the division first. If you do the division, it becomes the integral of 1 minus 1 over x squared plus 1. And then it's just x minus arctangent of x. So if the degree on top is bigger than or equal to, do the polynomial division, and then integrate the quotient plus the remainder divided by the divisor. All right, we've said plenty. I'll see you all next week, where we'll start talking about areas and volumes.